Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Oh, hi, Phil. Come on in.
Oh, hi, Mr. Wizard.
See that glass?
Yeah?
Well, come on over here. This is a
Matchbox.
an empty cover from a matchbox, you know. Playing card on the top. Golf ball. Pencil. You bring the pencil down here, flat, and give that thing a sharp blow right there, and watch what happens to the golf ball.
Do it?
Go ahead.
Wow. It dropped in.
Yeah. Pretty nice trick?
Yeah.
You want to get the cover over there?
Okay.
Now, why does that work that way?
Well, we studied about something like this in school. I
Yeah?
think I know what it is.
What?
Inertia.
What's that?
Well, it's a force. There are rules to it.
Yeah?
An object at rest tends to stay at rest unless influenced by an outside force. And, well, an object in motion tends to stay in motion unless interfered with.
You know who did all that?
Sir Isaac Newton?
Right, Sir Isaac Newton. Newton's laws of motion. And this is one of them, and that's what we're going to investigate today. But instead of just investigating, the laws just like that, we're going to play tricks with them. And here's the first one.
This reminds me of something I once saw.
What?
Where they pull a tablecloth away and all the dishes are still on the table.
Oh, you mean like over here? Tablecloth, dishes. All you'd have to do is take hold of the tablecloth and, like that, you mean?
Yes.
All right, before you leave today, I'll do it for you. In fact, not only would I do it, but I'll explain it, and maybe you can do it.
You sure?
Well, we'll try.
Am I responsible?
Remind me before you go. Before we start on that difficult one, though, let's do a simple one like this one. Now, you do this at home. You don't have to have the top of the matchbox. You can use just a lightweight box of some kind. Not lightweight, as you see in a minute, but for your purposes now. A card is on the top because this box doesn't have a top on it, see? If you have an ordinary box, you don't have to use the card. And then a ball that is fairly on the heavy side.
Yeah, that's...
Not really heavy, but heavy. You'll see why in a minute. Now put it up here like this, and get it directly over the glass, and give it a nice, good, fast whack. See how it's there. There she works. Now that's... Yeah, would you please? You said that was inertia. Okay, would you now explain to me why it is that I can take this piece of paper and... Glass stayed there.
Well, I know it's inertia.
Isn't this like the tablecloth?
Yeah, it's
And
the
the
same
food?
kind of thing, yeah.
Only this is a little piece of tablecloth and only one dish. Okay, you say that's inertia, the fact that I can pull it out.
That's right.
Okay, now then, would you please explain to me this? Now it's not coming out. Why not?
Well, you're not pulling it fast.
What's the speed got to do with it?
Well...
What?
It's, you have to pull it from underneath, well, this is heavier than the paper is.
Oh?
And, I mean, yeah, the water is heavier.
Yeah, the
than
water is
paper.
heavier than the paper. What's that got to do with it?
And when you pull it fast, the paper will stay there, and the glass will stay there, and the paper
Well, now,
will
you
move
remember
away.
when I told you about the ball and the glass and stuff, I said, for your purposes now, heavy, but it's not really heavy. That's not the important thing. Because what is, you say heavy, where does that word come from? What does that mean? What is the force that makes it heavy?
Oh, gravity.
Gravity. Isn't gravity pulling it down?
Yeah.
Isn't it sitting on the table?
Yeah.
Isn't the table pushing back up again so that gravity is now counteracted?
It is.
Well, then what's gravity got to do with it? We're not pulling it down or up. We're pulling it sideways.
Why does it work?
Yes, why does it work? It's not gravity. It's not the weight of something. Yet you seem to be right, isn't it? That the heavier the thing is, it stays there while the light thing goes. Well, in order to understand what it is that really makes this inertia effect, let's look at a special kind of inertia balance. There it is up there. See that? These are two hacksaw blades. See, and they're clamped down here on each side of this thing. And here's a little platform here with a hole in it. And when you pull it off to one side and let go...
It really moves.
Now, it moves because the hacksaw blades have a certain amount of elasticity, and here's a weight out here.
Yeah, and they keep on going back and forth.
Okay. Now, here's another weight with a string on it, and the hole in here that I can put a nail through here so that I can support this weight like this. Now, would you please vibrate this again and notice the speed with which it goes, you know, how its period of oscillation.
I can't even count it.
You know, quite fast.
Yeah.
Now, if I add this weight on here, is it going to go the same speed, faster or slower?
It should go slower, I think. There's more weight.
All right, try it.
4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
Now, you said more weight. Why did you say weight?
Well, you're adding to it.
Okay, the force of gravity
It's
pulling down here
and
is,
adding more weight to this platform.
However, now, if I have a string on here, you see, and if I take the string up here like this, I can hook it over that little thing like that, and now the weight that you said weight is still close to this, but it's now not supported there anymore, isn't it? Look.
Yeah, sure. The string is holding it up.
The string is holding it up. So now we don't have the weight on this platform, do we?
No.
Okay. Now let's do this again without this on here. Now you vibrate it once. You hear that rhythm?
Yeah.
Okay, now I'll attach this, take that nail out, and you do it again. Same rhythm?
Sounds pretty much the same to me.
But now it's not, couldn't be the weight.
Well then, you know, it isn't the weight.
No,
it's,
you know what it's called? Mass.
It's this thing.
Mass.
It's the mass.
Yes. Now what does that mean, mass?
What's the amount something has in it?
You mean like 7?
We're mass. Well, no, I mean, it's amount. That's just what it is.
It's stuff.
Stuff,
Yeah, okay. In this case, it is not weight, but the volume of the stuff and the fact that it has, in fact, when scientists define weight, their kilogram, for example, 1,000 grams, is defined in terms of its inertia, not its
because its weight is only the gravitational pull.
Right. If you took this up into outer space, what would it weigh?
Nothing.
Would it still have the same mass?
Sure.
Would this still vibrate at the same rhythm?
Yeah.
But no
So
weight.
it has nothing to do with the weight. Oh, so it works the same way
Like
with
the glass, yes. Now, you see why I say it's not weight, but the mass.
The mass. So the glass has more mass than the water than this.
And when you do these tricks at home, try to get a ball that has lots of mass.
It'd work better, wouldn't it?
And try to get the things between the ball and the glass with very little mass. So that will move, but the ball will not.
And the ball will drop.
Okay, and the same thing as the piece of paper. Okay. Now, when you get practiced, why does it move when you go slowly now?
Well, we haven't overcome the forces that are holding it back.
There's friction between the bottom of the glass and the paper. And as long as you move slowly, you have not exerted enough force so that this inertia will overcome the friction between the two.
So
but when you move it fast, the frictional forces inside the paper hold it together, but the force is now strong enough to overcome the friction, so it leaves the glass behind.
So it leaves the glass and pulls the paper.
So the way to do this is to pull it slowly. And now you can get up considerable speed once you get going, and then... And if you practice, maybe you could even get it so it's like that.
It's a little dangerous, though.
Well, at home, maybe you should practice with a tin can full of nails or pebbles or something, you see, so in case it spills.
It isn't quite so dangerous.
Quite so dangerous. Okay, now, what is it that makes these things work? Not weight,
Mass.
but mass.
The mass has to do with the inertia.
And when we pull the tablecloth out from underneath, it's going to be the same thing.
It should be.
But before we do that, maybe we better do some more practicing on various other kinds of inertia.
I hope so. I'm not quite ready to try
Okay, here's a brick. And I have a piece of ordinary baker store string in it. Now, would you take the string and slowly raise the brick? Is the string strong enough to support it?
Sure.
Okay, it is. Now, hold the brick a couple of inches off the blanket down there. And now, move your hand up fast.
Snapped.
You mean the brick now weighs more?
Well, the weight doesn't change.
What does?
Well, it must work somewhat the same as you say. The paper, when you pulled it slowly,
Yes.
it didn't change. But when it went fast, it did. Then the inertia was pushing against it, and it was...
In the one case, we have just the force of gravity when we pick it up slowly. Very little inertia, right?
Mm-hmm.
But now when you move fast, you combine the force of gravity pulling down and inertia at the same time as pulling in the same direction. The force
That's
of
right,
inertia.
because it's coming against it.
So this is why you can now...
Well, does it really become heavier for a second there,
No,
or is
not,
it just the
no,
forces
not
that
heavy.
make it
Heavy means gravity.
I mean,
it
the mass doesn't become
No,
heavy.
but it has inertia, and that's why scientists define it this way. It is a force, that helps break this. Okay, now try it again.
Slowly. And then
Slowly. Now wait. You didn't move fast enough. Wait. Get it up here. Make sure it stopped.
Oh, maybe that's what...
Now, there.
Oh, and then when I pull up, the inertia becomes greater.
Now, why? I was going to mention it over there, but I forgot it. Why? Where does this inertia come from, this force?
It's there.
Well, most of the time you study about it in school, yet you never really, think of where does it come from. See if this makes sense. Scientists think that perhaps this might be the answer. On this brick at the time when you pull it up, if you pull it up slowly, the force of the string is pulling up, gravity is pulling it down. Mm-hmm. Does the moon affect this brick?
Yeah, well, I know it affects the tides, high tide, low tide.
Yeah. So it's probably affecting this brick. How about the sun?
What? The sun affects the whole planet.
Yeah, and all the things on it, of course. So how about stars? Do they affect it?
I don't know.
Well, Newton, way back when he formulated these laws, realized that there was a gravitational force between all the things in the universe. One planet to the next planet, and one planet to the sun, and all the stars.
Makes sense.
So now let us say that we have forgotten gravity for a minute, pulling down. But all the rest of the forces on the universe, all the rest of the bodies in the universe, all around it, are all affecting this brick. Trying to pull it this way, this way, this way, this way, and they all are equal.
Well, then, you could let go of it and it would just stay there.
And what about it in outer space?
It does.
That's
You
exactly
float
what
around.
happens, isn't it? Now, if you give it a little push,
It
you've
starts to
suddenly
move.
given it a little extra force in this direction, so it would continue to
overcomes
move.
these and it
When you now give it a big, fast, quick push, you suddenly overcome the forces that are pushing in this direction for that instant.
Yeah.
So you get it so that it would tend to move.
go like that.
Anyway, this is one of the explanations that scientists feel that perhaps this may be an explanation
Well,
for
how
this.
come it won't work here?
What do you mean? Well, we have gravity, our big problem.
Oh, that's right. It's much closer, though.
Right. Because the Earth is so close, you forget about those other forces that
Well,
are so small
if we
compared
could
to.
kind of get right in the middle of everything, then...
Which is
would
kind
I
of
get
then
up-
perhaps where our galaxy is.
Yeah,
That's what maybe keeps it where it is.
maybe so.
Okay, how about, let's do another version of this. Have you ever noticed people in the store? Here's a paper bag. Would you fill it full of bricks?
Sure.
Well, or at least put these three in.
Going shopping.
Yeah, now instead of using the string this time, let's use the paper bag. Just grab a hold of the side of it here and pull up slowly. Slowly. Okay, no problem. I'll put it down, and now use the force of inertia. Pick it up quickly.
Rip.
Try the other side. There.
Rip.
You notice the difference? In fact, this happens to women sometimes when they go shopping at the supermarket. They get a big bag full of groceries, full of cans and things. And if you try to pick it up from the top and do it too quickly...
All over the floor.
all over the floor. So the answer is if you are going to pick it up by the top, pick it up slowly. Now this force of inertia was pulling down in this direction. Let's do the same thing, but support it down a different way, over here with a couple of more bricks. See this little platform?
Yeah.
Roller skate. Brick. Another brick.
What are you building?
Well, this now has inertia, doesn't it? This mass that I put up here. Whoa!
Oh!
See what happened? The wheel hit the edge here,
The edge.
and we destroyed our low friction.
But how come it, like, we were just doing it now, and it didn't go off the edge?
Yeah, it doesn't move. Now, why? How much friction is there in the roller skate wheels? Very little. In fact, that one isn't even touching.
Yeah.
So that this mass now, because of its inertia, will stay there while we push the thing underneath, just as though I were holding it.
Oh, so this really is moving. It's just the ground is
The
really
ground is
underneath.
moving. In fact, this might perhaps help you understand a seismograph. You know what that is?
Scientists use that to measure earthquakes, don't
Right. To measure the movements of the earth, a tremor of some kind, either from the, slippage or a volcano exploding someplace, or perhaps an atomic bomb or something like this. Well, imagine that this is the earth down here. Then if you suspend a large weight so that its gravitational forces are counteracted, and you now put a pointer on here, and now coming up from the earth, you now put a piece of paper with, smoke on it or something. Now, if the earth moves, what would happen to the pointer?
Well, the pointer would stay still, but the paper you put on the earth would move, and you get. So that's what the jagged lines
Right, that's
are.
where the jagged lines come. See, there's an earthquake, and we could record it right here.
So is this how it works?
That's the principle behind it. Yeah. Now, have you ever driven a car? You're too young to drive, but have you ever practiced it or anything?
Well, up in the country sometimes.
Yeah.
On, old roads and things.
Yeah.
My father lets me.
Lets you try. Well, let's see. Good, because I wanted to know if how fast did you go?
I don't know.
20, 30 miles an hour?
35, 30, I don't know.
When you got in the car, when your father got out and went around, and he sat in that seat, and you sat there in the driver's seat, did he tell you to, okay, get going 35 miles an hour, and what you put your foot on the gas, and zing, all of a sudden you were going 35?
No,
Why not?
Went slowly.
Yeah, why? Well, what's the point of, if you're going to go 35, why not go 35?
I couldn't if I wanted to. You can't just get in the car and go 0, 35.
Why not?
Inertia.
Inertia, that's right. In fact, we can use this roller skate as a car and see why it is that you have to start up slowly. And we can kind of make a measurement of the effective force of the inertia. Let's assume that this roller skate is a car, and that this rubber band here is the motor, the engine. See, now I have a little hook there that we can hook on the engine. So you could, by how far you stretch it, why, this is going to be a measurement of starting friction and inertia. So we can't assume that it is all inertia. I'll put the brick on here to give it some mass, and I'll put a pencil right here by the front wheels. Now you stretch the rubber band so it's just barely tight, and now slowly pull the rubber band, and we'll put a second pencil here at the point where the cart begins to move. Right
there.
Right about there? Now try it once again to make sure that that's not an accident, because if there's a little piece of sand or something down here, it would throw all our readings off. Someplace in there? Okay.
Almost the same.
Now this is like a car. If you want to start the car up, you'd have to have that much force on it before the car even moves to overcome inertia.
Yeah, so right away, so you can't go just zoom.
Right, you can't. Now, let's make this car into a truck. Is there going to be more force to get it started or less?
Sure.
Okay, here's another...
More mass.
More
not
mass.
Weight,
right,
mass.
More mass. Go ahead, try it once and see if it takes...
Holy.
About in there?
It's about there.
Let's try it again.
Check it now. Ready? Whoa.
A little more, huh?
A little bit more, yeah.
Okay. So now, is this true? Is this what happens with a truck? Does it take more force to get the truck going?
Sure. I mean, if you're in back of a truck and stopped, by the time it gets going, it's
Right,
might
takes
just
a
turn
long,
red again.
yeah, long time, especially if it's full of sand or rocks or things. And how about a train?
Even slower when they pull out of the station. Very,
Yeah, very slow.
It's a long while before they get going to
Right,
top
because
speed.
they have a tremendous mass to get moving.
Mm-hmm.
Okay, well, now that's why you can't step on the gas and suddenly go 35. If you do sometimes, the wheels spin around, don't they?
That's right. You just don't move. You just stay in one place.
Because of the great mass of the thing. Okay. Well, now, all of the forces that we've, or all the inertial effects and tricks that we've done so far have mostly been with things that were at rest. And Newton said that they would tend to stay at rest. Now, what was the second part?
Oh, an object in motion would tend to stay in motion.
Okay, well, now let's try doing some experiments with that. The simplest one is this. Ball, steel ball, so it has plenty of mass. You could use a golf ball, too. And a box with one end cut out. If I put it here and get the box moving, I'll overcome the inertia of the ball and get it to move with the box. Then I'll simply stop.
object in motion tends to stay in motion.
So the ball continues.
It meant another force, though, my hand.
Your hand. So this now is an example of force continuing, or the mass continuing because of its... I'm not pushing it, see? I simply stop. So.
Well, this happens in a car even sometimes.
That's right, it does. It will, in fact, let's see what happens in a car. Car. Brick wall.
Friends of yours?
Well, little clay figures to kind of show you what can happen. This is one of those cars, you know, that inertial cars, as a matter of fact, aren't they called? Inside there's a little sort of a heavy weight, and once you get it moving, why the car continues to spin. So ordinarily, if you were driving along in the car and you wanted to stop, you'd put on the brakes and gradually come to a stop. Okay, this time, get it going and let it hit the brick wall at high speed and see what happens.
Right through the windshield.
Yes, right through the windshield. It's kind of horrifying, isn't it?
Yeah, well, that's unfortunately what happens, though.
Yes. Now, why?
Well, both the car and the people were moving along.
Right, like the ball in the box.
Yeah, and all of a sudden the car stopped, but they kept on going.
Right, just like the ball. They kept right on going. In fact, they could, you know, fly right through the windshield and all the rest of it. So now, what do you do about this?
You stop them.
Well, in other words, the first thing you do is you don't try to hit any brick walls. You slow down, and you do it slowly, so that you will stop with the car. Okay, then, for emergency purposes, what do? Seat belts.
Oh, and that would hold you in, so when you came to a
like
crash, be held back.
In fact, many people are injured by just moving forward and hitting their head on the windshield. And the seat belt, of course, prevents this from happening because you stop with the car when you have a seat belt on. So that's a good example of inertia, unfortunately, because it can be very dangerous. And you find it other places. Have you ever noticed how when the car goes around a corner, you move over to one side of the car?
Yeah, it always happens at a big turn or something. You know, you're always leaning. And
well, you tend to go in the same direction as you were, and the car is moving, so that means that you have to move in.
If the car was turning like this, you'd be going...
Well, you lean like that to counteract the force that is tending to keep you going in the same direction. In fact, this aspect of inertia is so much a part of your everyday life and your experience that you never really stop to think about it. Maybe I can make you think about it up here with a ball. See this? Here's some steel balls down here like this.
Yeah.
And this is in an incline, so that when you put them up here between these two strips, to get the ball started.
Roll down to the bottom.
Yeah. Now, what are the forces that are acting on this ball? Why does it continue to go like this?
Oh, well, it's inertia. Once it's overcome, it's...
well, this is gravity, first of all.
Yes.
Gravity.
It's pulling it down because it's on an incline.
But gravity's pulling it down this way.
Yeah.
And the force of this thing, because I have it built up this way, is now making it go in that direction. Okay, now...
What happened?
What do you mean, what happened? I rolled the ball down the incline.
Yeah, but you were rolling it down before, and so I went to one side.
That's inertia.
No.
Huh?
No, you're putting a
I don't understand what's the matter with you. It's going along perfectly fine here. What's the matter with you? Hmm? Would you like to try it? Go ahead, try it.
Sure. Well, it was doing that.
Perfectly all right to me. I don't see what you're so...
That, you just made it go to one side.
What?
Look, it was...
Here.
Well, there evidently is another force or something is going on.
Why? Why are you so amazed? What's the matter?
Well, because normally it would go down a straight line.
Then what happened?
And then it came halfway down, and then it...
And moved over like that?
Went over to one side.
You mean like that?
No, what's the other side?
You mean it makes a little curve in there?
Yeah.
And you don't think that that's right?
Well, there must be some kind of a twist or something in the tape or something that's making it...
In other words, you are so accustomed to having things continue in a straight line that when they move off of the straight line, you know something's wrong because you know that inertia forces say that it's supposed to go on. Well, what do you suspect it is? What is that ball made of?
Steel.
Steel. Besides gravitational forces and inertia, what other kind of forces could make that ball move?
Oh, a magnet.
A magnet, huh? Oh. Think you're pretty smart, eh?
An electromagnet.
Mhm.
Oh, and a foot switch.
And a foot switch.
No wonder I couldn't see what was going on.
Here, you work the foot switch. Now turn it on. Okay, now turn it off. Get the idea?
Yeah, I think I do. So every time that I rolled it down, you took your foot off.
Right.
Every time that you rolled it.
And of course it was turned around here like this so that as it went by here, it affected the ball as it went down. Okay, well now, you see how much you take this inertia for granted?
Sure.
You think you now have had enough experience with inertia to pull the tablecloth out from under the food?
Hope so.
All right, let's try it.
Oh, I don't know.
See, here's a pitcher of water, a glass of water, an apple, salt, pepper, bacon and eggs, plate, knife and fork. And according to the glass of water and the piece of paper over there, all we have to do is give it a good old jerk fast.
You sure it's going to work?
Well, I don't know.
It should work.
There's only one way to find out, and that's to give it a good pull. You ready?
I'm ready. But,
All right.
It worked.
Okay, now you want to try it?
Okay.
Now, here's what, if you want to try this at home, and it's a good trick, a very famous trick, which many people try to do and then, you know, they don't work too well. You must have a special kind of tablecloth that is kind of like the paper, very smooth, so that you have very little friction between this and these items. Then make sure that it does not have a hem in it. Because you can see, with the cloth moving along, what happens when the hem comes along?
Oh,
It'll tip things over. So then also be sure and try to do this on a relatively smooth table so that you keep the frictional forces between the tablecloth and the table as small as possible. And the stuff that you set on the table should they be heavy, quote unquote, or should they be light, quote unquote?
heavy, quote unquote.
Now, what do you mean by quote unquote? Should have mass,
It
right?
should have the mass.
Okay, you get around over here. And when you pull in the same plane. Don't pull up, don't pull down. Pull this way.
Sure you want me to do this?
Well, you might as well. Okay?
What kind of moves? There's such a few
Now,
dishes.
get your hand out here as far as, because all you have to do is move the cloth this much.
You sure this is going to work?
I don't know, we'll try. It worked for me. So get up here like this and pull, but don't try to move your feet. Okay, here we go. Take it, fast.
It worked!
Congratulations.
Wow.
Can you try it again?
Watch Mr. Wizard is presented each week at this time by the Public Affairs Department of the NBC Television Network in cooperation with New York University.